Testing a grounding system by touching an energized conductor to electrical metallic tubing, or EMT, is an incorrect and highly dangerous procedure. It can lead to electric shock, serious injury, or even death. The correct procedure to test a grounding system involves using a multimeter to measure the resistance between the grounding conductor and the earth ground rod. The resistance should ideally be less than 25 ohms. If the resistance is higher than 25 ohms, it indicates a problem with the grounding system that needs to be addressed and repaired. There are several reasons why touching EMT to an energized conductor is an incorrect and dangerous practice. Firstly, it poses a significant risk of electric shock. The energized conductor can transmit electricity to the EMT, and if someone is touching the EMT, they can become part of the electrical circuit, leading to a potentially fatal electric shock. Secondly, this method is an ineffective test of the grounding system. Touching the EMT to an energized conductor does not provide any meaningful data or information about the grounding system's ability to effectively clear faults and protect equipment and people. Thirdly, this method is incredibly dangerous. It can create a high current path, potentially leading to a fire or an explosion. This is because the fault current may not be properly controlled, and the resulting arc flash can be extremely hazardous. Fourthly, it violates electrical safety codes. The National Electrical Code, or NEC, and other electrical safety codes explicitly prohibit intentionally grounding energized conductors to EMT or any other grounding path. This is because it creates an unsafe condition and increases the risk of electrical hazards. A cost-effective and safe way to test a grounding system is to use a multimeter to measure the resistance between the grounding conductor and the earth ground rod. This method provides accurate results and does not pose any safety risks. To perform this test correctly, firstly, ensure that the power to the circuit is turned off to prevent electrical shock. Secondly, locate the grounding conductor, which is typically a bare or green wire, and the earth ground rod, which is usually a metal rod driven into the ground near the building's service entrance. Thirdly, set the multimeter to measure resistance, usually indicated by the ohm symbol. Fourthly, connect one lead of the multimeter to the grounding conductor and the other lead to the earth ground rod. Fifthly, read the resistance value displayed on the multimeter. The resistance should be less than 25 ohms. If the resistance is higher than 25 ohms, it indicates a problem with the grounding system. This could be due to several factors, including corroded connections, loose wiring, or a damaged ground rod. The high resistance prevents proper fault current flow, increasing the risk of electrical shock and equipment damage. In such cases, further investigation is needed to identify the cause of the high resistance and implement appropriate repairs. This may involve cleaning and tightening connections, replacing damaged wiring, or driving a new ground rod. Understanding the principles of grounding is crucial for electrical safety. The grounding system provides a low impedance path for fault current to flow back to the source, allowing the circuit breaker or fuse to trip and to energize the circuit. This helps to prevent electrical shock and minimize damage to equipment. A properly functioning grounding system is essential for protecting people and property from the hazards of electricity. It is also important to regularly inspect and test the grounding system to ensure that it is functioning correctly. This can be done by a qualified electrician using appropriate test equipment. In addition to testing the resistance of the grounding system, it is also important to visually inspect the grounding connections for any signs of corrosion or damage. Corroded connections can increase resistance and compromise the effectiveness of the grounding system. Loose wiring can also create a hazard by interrupting the grounding path. By following these simple steps, you can help to ensure that the grounding system is functioning correctly and that your electrical system is safe. Remember, electricity is a powerful force that can be dangerous if not handled properly. Always take precautions when working with electricity and consult a qualified electrician if you have any questions or concerns. Grounding is the intentional connection of a neutral conductor or equipment enclosure to the earth. The purpose of grounding is to limit voltage buildup and provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to trip. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding involves connecting the metal enclosures of electrical equipment to ground. This helps to prevent electric shock by providing a low impedance path for fault current to flow back to the source. System grounding involves grounding the neutral conductor of the electrical system. This helps to stabilize the voltage and prevent overvoltages. The NEC provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that electrical systems are safe and reliable. The NEC specifies the size and type of grounding conductors that are required for different types of electrical systems. It also specifies the methods for grounding equipment and systems. The NEC also addresses the issue of ground resistance. Ground resistance is the resistance of the earth to the flow of current. The NEC requires that ground resistance be low enough to allow fault current to flow back to the source and trip the overcurrent protective device. The NEC also provides requirements for grounding electrodes. Grounding electrodes are used to connect the grounding system to the earth. The NEC specifies the types of grounding electrodes that are permitted and the methods for installing them. Grounding is an essential part of electrical safety. By properly grounding electrical systems, we can help to prevent electric shock and protect equipment from damage. It is important to follow the requirements of the NEC when grounding electrical systems. This will help to ensure that the electrical system is safe and reliable. Some additional points to consider are: firstly, all electrical work should be performed by a qualified electrician. Secondly, always follow the NEC and other applicable codes and standards. Thirdly, never work on electrical equipment while it is energized. Fourthly, always use appropriate personal protective equipment, such as gloves and safety glasses. Fifthly, if you are not comfortable working on electrical equipment, call a qualified electrician. Testing grounding systems is essential for maintaining electrical safety. Proper grounding ensures a low impedance path for fault currents, allowing overcurrent protection devices to quickly trip and minimize the risk of electrical shock or equipment damage. Here's a breakdown of essential testing methods and considerations. Firstly, visual inspection. Regularly inspect grounding conductors and connections for corrosion, damage, or looseness. Corrosion can significantly increase resistance, while loose connections can interrupt the grounding path. Secondly, continuity testing. Use a multimeter to verify the continuity of the grounding path from equipment enclosures to the grounding electrode system. This ensures that a continuous low impedance path exists. Thirdly, ground resistance testing. Measure the resistance of the grounding electrode system to earth. This is typically done using a 3-point fall of potential method. The NEC recommends a ground resistance of 25 ohms or less, but lower values are often desirable for sensitive electronic equipment. Fourthly, ground impedance testing. Measure the impedance of the grounding path, which includes both resistance and reactance. This provides a more comprehensive assessment of the grounding system's effectiveness, especially in systems with long grounding conductors. Fifthly, touch potential measurements. In critical applications, measure the touch potential, which is the voltage difference between a grounded object and the surrounding earth. This helps ensure that personnel are not exposed to hazardous voltages during fault conditions. Sixthly, step potential measurements. Measure the step potential, which is the voltage difference between 2 points on the ground surface a meter apart. This helps identify areas where personnel could be exposed to hazardous voltages while walking during a fault condition. Seventhly, clamp-on ground resistance testing. Use a clamp-on ground resistance tester to measure the ground resistance without disconnecting the grounding electrode. This method is useful for quickly assessing the ground resistance in existing systems. Eighthly, insulation resistance testing. Test the insulation resistance of conductors to ground to identify potential leakage currents. High leakage currents can indicate insulation breakdown and increase the risk of ground faults. Ninthly, load impedance testing. Measure the impedance of the electrical load to ground. This helps identify potential sources of ground faults and ensure that the grounding system is adequate for the connected equipment. 10thly, documentation. Maintain detailed records of all grounding system testing and inspections, including dates, test results, and any corrective actions taken. This documentation is essential for demonstrating compliance with safety standards and for tracking the performance of the grounding system over time. Remember, it's always a good idea to consult with a qualified electrician or electrical engineer for detailed guidance on grounding system testing and maintenance. Proper grounding is critical for ensuring the safety of electrical systems and protecting personnel from electrical hazards. It is important to note that the NEC serves as a foundation for electrical safety in the United States, and understanding its requirements is paramount for electrical professionals. The NEC is regularly updated to address new technologies and safety concerns, so staying current with the latest edition is essential. The NEC is divided into chapters, articles, and sections, each addressing specific aspects of electrical installations. For example, Chapter 2 covers wiring and protection, while Chapter 3 deals with wiring methods and materials. Grounding is a recurring theme throughout the NEC, with specific requirements detailed in Article 250. This article covers the general requirements for grounding and bonding, including the types of grounding systems permitted, the sizing of grounding conductors, and the methods for grounding equipment. The NEC also addresses the issue of bonding, which is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding is essential for preventing voltage differences between metal parts, which can pose a shock hazard. The NEC specifies the methods for bonding equipment, including the use of bonding jumpers and grounding bushings. The NEC also addresses the issue of surge protection. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges, such as those caused by lightning or switching transients. The NEC specifies the requirements for installing SPD, including the location and type of SPD required. The NEC also addresses the issue of hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust are present. The NEC specifies the types of electrical equipment that are permitted in hazardous locations, as well as the methods for installing them. The NEC also addresses the issue of emergency systems. Emergency systems are electrical systems that are designed to provide power during a power outage. The NEC specifies the requirements for emergency systems, including the types of equipment that are required and the methods for installing them. The NEC is a complex and comprehensive document, and it is essential for electrical professionals to have a thorough understanding of its requirements. The NEC is available for purchase from the National Fire Protection Association, or NFPA, and it is also available online. By following the requirements of the NEC, we can help to ensure that electrical systems are safe and reliable. A proper understanding of electrical theory is essential for anyone working with electrical systems. Electrical theory provides the foundation for understanding how electricity works and how to safely install and maintain electrical equipment. Firstly, basic electrical concepts. Voltage. Voltage is the electrical potential difference between 2 points. It is measured in volts. Current. Current is the flow of electrical charge. It is measured in amps. Resistance. Resistance is the opposition to the flow of current. It is measured in ohms. Power. Power is the rate at which electrical energy is used. It is measured in watts. Secondly, Ohm's law. Ohm's law states that the voltage across the conductor is proportional to the current flowing through it. The formula for Ohm's law is volts equals current times resistance, or volts equals amps times ohms. Thirdly, series and parallel circuits. Series circuits. In a series circuit, the current is the same through all components. The voltage is divided among the components. Parallel circuits. In a parallel circuit, the voltage is the same across all components. The current is divided among the components. Fourthly, AC versus DC. Alternating current, or AC. Alternating current is electrical current that periodically reverses direction. Direct current, or DC. Direct current is electrical current that flows in one direction only. Fifthly, transformers. Transformers are used to step up or step down voltage. They work by transferring electrical energy from one circuit to another through electromagnetic induction. Sixthly, three-phase power. Three-phase power is a type of alternating current power that uses 3 conductors to deliver power. It is more efficient than single-phase power. Seventhly, grounding. Grounding is the intentional connection of a neutral conductor or equipment enclosure to the earth. The purpose of grounding is to limit voltage buildup and provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to trip. Eighthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. Ninthly, wiring methods. There are many different wiring methods that can be used to install electrical wiring. The NEC specifies the permitted wiring methods for different applications. Tenthly, electrical safety. Electrical safety is essential for anyone working with electrical systems. Always follow safe work practices and use appropriate personal protective equipment. By understanding these basic electrical concepts, you can safely install and maintain electrical equipment. Always consult a qualified electrician if you have any questions or concerns. Testing electrical circuits safely and effectively requires understanding the proper procedures and using the right equipment. Firstly, always de-energize the circuit. Before testing any electrical circuit, always turn off the power at the circuit breaker or disconnect switch. Verify that the circuit is de-energized using a voltage tester. Secondly, use appropriate personal protective equipment, or PPE. Wear safety glasses, gloves, and other appropriate PPE to protect yourself from electrical hazards. Thirdly, use a voltage tester. A voltage tester is used to verify that a circuit is de-energized and to measure the voltage in a circuit. Fourthly, use a multimeter. A multimeter is a versatile tool that can be used to measure voltage, current, resistance, and other electrical parameters. Fifthly, use an insulation resistance tester. An insulation resistance tester, also known as a megameter, is used to measure the insulation resistance of conductors and equipment. Sixthly, use a ground resistance tester. A ground resistance tester is used to measure the resistance of the grounding system. Seventhly, follow safe work practices. Always follow safe work practices when working with electrical circuits. Never work alone, and always keep a safe distance from energized equipment. Eighthly, verify your readings. Always verify your readings with a second meter or by comparing them to known values. Ninthly, document your results. Document your results and keep a record of your testing activities. Tenthly, seek professional help. If you are not comfortable testing electrical circuits, seek help from a qualified electrician. Electrical safety is paramount, and it's always best to err on the side of caution. There are a few critical aspects of electrical safety that every technician should know. Firstly, lockout-tagout or LOTO procedures are essential for preventing accidental energization of equipment during maintenance or repair. Always follow LOTO procedures to de-energize and isolate electrical circuits before working on them. Secondly, arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. An arc flash can cause severe burns, blindness, and even death. Always wear appropriate arc flash PPE when working on energized equipment. Thirdly, ground fault circuit interrupters, or GFCIs, are life-saving devices that protect against electrical shock. GFCIs are required in wet locations, such as bathrooms and kitchens. Fourthly, electrical hazards can be caused by several factors, including faulty wiring, overloaded circuits, and damaged equipment. Regularly inspect electrical equipment for signs of damage and repair any problems immediately. Fifthly, personal protective equipment, or PPE, such as gloves, safety glasses, and arc flash suits, is essential for protecting against electrical hazards. Always wear appropriate PPE when working with electrical equipment. Sixthly, safe work practices, such as keeping a safe distance from energized equipment and never working alone, can help to prevent electrical accidents. Seventhly, emergency procedures. Know the emergency procedures for electrical accidents, such as how to shut off the power and how to provide first aid to someone who has been shocked. Eighthly, electrical codes and standards. Electrical codes and standards, such as the NEC, provide detailed requirements for electrical installations. Staying up to date on the latest codes and standards is essential for electrical safety. Ninthly, training and education. Electrical safety training and education are essential for all technicians who work with electrical equipment. Make sure you receive adequate training before working on electrical equipment. Tenthly, common sense. Electrical safety requires common sense and a healthy respect for electricity. Never take shortcuts or ignore safety procedures. By following these electrical safety tips, you can help to prevent electrical accidents and injuries. Remember, electrical safety is everyone's responsibility. Testing methods vary depending on the type of system and the goal of the test. It is also important to understand the equipment being used. A multimeter is a versatile tool but requires careful setup and interpretation. Grounding testers are designed for specific grounding system analysis. Insulation testers require understanding of voltage levels and safety precautions. The proper test instrument for the job must be used, and you should also familiarize yourself with the limitations of the instrument. In conclusion, safety is paramount when it comes to electrical work. When in doubt, always consult a qualified electrician.